Have you ever used one of those weightlifting machines at the gym and wondered how much weight you're actually lifting? Like, for example, on a lat pull down machine, if you use the pin to select 50 pounds based on the machine's pulley and cable system, are you actually lifting 50 pounds or less? Well, in this video, we're going to dive into exactly that and figure out what the answer is. Now, let's just take a look at the lat pull down machine that we referenced. So, the way this is set up is you have a weight stack on the machine, and you have a cable running from the weight stack through two pulleys, which are on the top arm at the top of the machine, and running down to whatever attachment that you want to hook onto it. And this system could be as simple as two pulleys, or it could get more complex, have three or four, even more pulleys. For a cable curl machine, the system looks a little bit different from the lat pull down. So you have the weight stack, and then a cable running from the weight stack through a pulley at the top of the machine for support, through another pulley at the bottom of the machine, represented by the second pulley here. And then, of course, the cable comes out through the last pulley, and then it gets hooked onto whatever attachment you choose for the movement. Now, in order to understand the physics of weightlifting machines and how much weight is actually lifted by you, the user, we're going to look at free body diagrams of these machines. Free body diagrams from a basic statics and physics review are just diagrams that you draw of a specific mechanical system in order to analyze forces that are acting directly on a specific part of the system. And free body diagrams are important because you have to take away all constraints and supports from whatever part of the system you're looking at, and it simply just allows you to look at the forces and the moments, which are rotational forces or torques acting on the system. So that's a nice way to see what kinds of forces act on each particular part of a system. So for our first example, the lat pull-down machine, the free body diagram would look something like this. You have the first pulley represented here in the green, which is the left pulley, the leftmost pulley, and you've got two forces acting on it. So you have a vertical downwards force, which is 20 kilograms. Technically, the tension force acting on the cable would be a value in newtons, but for simplicity, we'll just keep it in kilograms. So you have a downwards force acting on the left side of the pulley on this cable here, 20 kilograms, which is what holds the weight stack up. And then the force to counterbalance this downwards motion here and force is a tension force in the horizontal direction towards the right, towards the second pulley. This keeps the system in balance. So 20 kilograms from the weight stack, and then a tension force on the horizontal cable to keep the system in balance. Now, you have to sum forces and moments to determine the forces and moments acting on this particular system. But in our case, with this example, we're just going to sum the moments since that is the most useful. And the sum of the moments would just be basically the sum of the torques in both the counterclockwise and clockwise directions. So the clockwise direction will be taken as positive. So force 1 multiplied by the radius of this pulley gives a moment in the clockwise direction. And then 20 kilograms times the radius of the pulley, same radius, gives you a moment in the counterclockwise direction, so a torque force in the counterclockwise direction. So once you resolve this equation, you can see that F1 equals 20 kilograms. And this makes logical sense because if you use a cable to hoist up a 20 kilogram weight using a pulley, the tension force that you're going to have to exert on this side of the pulley, on this cable, is going to have to equal the amount of force that the weight of the weight being hoisted up exerts on the cable itself. And when looking at this makes logical sense because if we're using a cable and a pulley system to hoist a weight up, say a weight of 20 kilograms, then in order to keep this weight up and prevent it from falling, the user is going to have to exert a force of also 20 kilograms on the opposite end in order to hold it up. So this makes sense. Now looking at the second pulley, we have a similar situation. F1, again, just in the opposite direction, and then the output force, which is what the user exerts onto the cable with whatever attachment that he's going to use for the cable machine. So again, summing the moments, you have the same situation, same answer. F out equals F1. So your output force, as we suspected from visual analysis, is indeed the same as the force exerted by the 20 kilogram weight. So if you want to hold a 20 kilogram weight on this end, you have to exert 20 kilograms of force. Now let's look at a more complex free body diagram like that of the cable curl machine or the tricep pushdown machine. Okay, now if we look at the free body diagrams of the pulleys, it looks a little bit different. And now we do the sum of the forces, and the y direction being positive, which is the vertical upwards direction. And then we do sum of the moments again as well. Some of the forces are not really useful to us because we're not trying to solve for all of the forces acting on the pulley. We're just specifically interested in the forces that are exerted by the cable on the sides of the pulley. So in this case, F1, that's what we're interested in. From the sum of the moments, F1 equals 20 kilograms. And then we look at the second pulley. We have a similar set of equations. F1 again in the opposite direction from this pulley because it's still the same cable on this side. And F1 equals F3 from the sum of the moments. F4 is just a supporting weight, and we are not interested in that. And lastly, the last pulley on the right, we have a similar situation once again, F3, which is this cable, just in the opposite direction because we're looking at the other pulley, and F out, the output force by the user on the cable. So once again, summing forces and moments, we see that F out equals F3, which also equals F1. Once again, to summarize, if a certain weight is exerting a tension force on the cable through a system of pulleys, the force required to be exerted on the cable at the opposite end of the pulley system in order to hold the weight up equals the force that the weight exerts on the cable at the opposite end. And the important key to notice here is that the cable moves the weight, not the pulleys. Now, in this scenario, it's a little bit different where you have the pulley directly lifting the weight. Instead of the cable lifting the weight, the pulley now assists in lifting the weight. Now this is where things get a little bit different. Some machines in the gym are set up like this as well, where you have a cable on the top of the machine for support. That's where it's anchored into. And then that cable runs down and around a pulley, and the pulley is attached by another cable to the weight stack. And this pulley is what does the actual lifting of the stack. So now, if we look at the free body diagrams of these two pulleys, you can see that our scenario is a little bit different here now. Now, instead of just a support weight acting on the pulley, which is where the pulley would be anchored into the machine at the top or the bottom, the pulley is now experiencing the direct force of the weight that is selected by the pins. And you can see also, in addition to that, you have F1 and F2, the tension forces from the cable. So if we sum those forces up, we have the equations like this, and we also do the sum of the moments once again. F1 does equal F2 because of the sum of the moments. Now if you substitute F1 equals F2 into this sum of forces equation, you can see that now you have 2F2 minus 20, or 2F2 equals 20. So this tension force in both of these cables is half of the weight, so 10 kilograms, which makes sense because you have 10 kilograms in this cable and 10 kilograms in this cable. Both of those add up to 20 to hoist the 20 kilogram weight. Now, if we just take this cable, represented by F2, and run it around the second pulley and down, which is where the user would be exerting the force with the attachment, you can see that F2 does equal F out, which is your 10 kilograms of force. In this example, with the pulley hoisting the weight, the user exerts the amount of force equal to half of the amount of weight that the weight stack is set to. So if you put your pin on 20 kilograms, you're actually only exerting 10 kilograms of force to lift that 20 kilogram weight with this particular machine. Additionally, if we go ahead and add another pulley to this machine, the result will still be the same, but we'll prove it with an additional free body diagram with that of the second pulley. So if we remember from the last diagram, F2 right here represents the force, the tension force on this cable, and then F out is going to be your output force. As you can see, with this setup, with an extra pulley, the force output is the same. It's just changing where the force is coming from, and it's just using an extra pulley to add fluidity of motion to the exercise. Lastly, we'll look at one more example, which is going to be a system of pulleys where 2 pulleys are now lifting the weight instead of just 1 pulley. And we're going to prove that each of these 25 Newton forces are acting on each of the 4 cables. In our case, we'll just simplify it from 100 newtons to 100 kilograms to just keep the unit of measuring kilograms. But force should technically be measured in newtons, as mentioned earlier. For the free body diagram for the large pulley, we can see the 2 tension forces on the 2 cables running along its sides, and then a third tension force, which is what the smaller pulley exerts onto the larger pulley to hoist the weight. And of course, the weight pulling down on the pulley of 100 kilograms. Second free body diagram is that of the smaller pulley. So that force right here is now a downwards force being pulled by the larger pulley. And then the 2 tension forces from the 2 cables around the smaller pulley. Using free body diagrams once again, we can see that F1 equals F2 due to sum of moments. And then we have a slightly different equation now for the sum of the forces. And we'll see that F1 and F2 are 25 kilograms and then F3 is 50 kilograms because 25 kilograms on each of the cables running through the large pulley and then an additional 50 to support the last 50 kilograms being exerted by the small pulley. For the second one, same free body diagram and equations as before. And we can see that 2F2 plus 2F4 now equals 100 due to substitution. And you can see, of course, that F3 is 50 kilograms, and these two are both 25 kilograms worth of tension force. And this is what hoists the system now this time. So 4 cables, you can see, are directly contributing to lifting this weight. So instead of just 2 cables lifting the weight with 1 pulley, you now have 4 cables assisting in lifting the weight with 2 pulleys. So now your output force is 25 newtons or 25 kilograms in our example. So 25 newtons of force to lift a 100 newton object. And in summary now, you can say that only if the pulley lifts the weight do you have force distribution and assistance. So if it's just a cable lifting the weight, then whatever the weight is, you have to exert that same amount of force to lift the weight up. So if you use a lat pull down machine, and you can see on the machine that the cable directly lifts the weight with only a pulley at the top of the machine, and there's no pulley near the weight stack to lift the weight. If you put the pin at 50 pounds, then you have to actually exert 50 pounds of force to go ahead and lift the weight stack. You can even test this out with your own body weight if your lat pull down machine goes that high. If you weigh 150 pounds, put the pin at 150 pounds, and then just hang on the handle with all of your weight pulling down on the handle and see if it starts to budge. If it just barely budges, then you can tell that the amount of force required by you to output equals the amount of weight that you select on the machine. So with 1 pulley lifting the weight, it's half of the original force output required as we saw with our equations. And then 2 pulleys, it's 1/4 of the force output, and so on. So if you continue to add pulleys, your force output is 1/2 times the number of pulleys that you have. So if you have 10 pulleys lifting the weight, then that means that you have to exert 1/20th the amount of force that the weight itself exerts onto the cable. So if you're trying to hoist a 1,000 pound weight and you're going to use 10 pulleys to do so, that means that the amount of force that you need to exert to hoist that 1,000 pound weight is going to be 1/20th of 1,000, which is 50 pounds of weight of force to lift the 1,000 pound weight. Hopefully that helped you out, and hopefully you kind of have an idea now for next time when you go to the gym. You can see how much weight, how much force you're actually exerting to lift the weight based on how the machine is set up. So don't think that just because you put the pin at 40 pounds to do tricep pushdowns, that you're actually exerting 40 pounds of force with your triceps, because you might only be exerting 20 pounds, and that depends on if the pulley is lifting the weight stack directly or if the cable is directly pulling up on the weight stack with only the pulley up on the top of the machine for support. So now you can lift a little bit smarter, hopefully, next time you go to the gym.